looking at methods for solving systems of equations that have more than two equations, but still just linear equations. Before we start that, I'd like to go over some rules that we will use to work on these systems. These are called elementary operations, and there are three of them. The first one is that I can interchange any two equations. Okay, the order of the equations in a system doesn't have any bearing on the solution, so if I want one particular equation to be the first one, I just move it up to the top. My second rule is that I can multiply any equation by a non-zero constant. You've done this already when you are working on systems of two equations. Multiply one by a non-zero constant to get one variable to cancel itself out. So even in larger systems, we can still do that. And then my third rule is a little more complicated. I can replace an equation with the sum of itself and a non-zero constant multiple of another equation. Okay, now that may sound a little bit complicated, so I'm going to show you an example of that. It's really not complicated at all. Let's say I have an equation x equals y. And I have another equation a equals b. Now in this example, it's not going to make much sense to do what I'm doing, but it's just an example of this. So I'm going to replace this equation in my system with the sum of itself and a non-zero constant multiple of another equation. So I'm going to take a equals b and multiply it by 3. So now I have 3a equals 3b. And this operation says that I could add 3a to this side and 3b to this side because they're the same thing. We know that 3a is equal to 3b, so over here I would end up with x plus 3a equals y plus 3b. So if I have two equations, I can add the two left sides together and I can add the two right sides together and still have an equation that is equivalent because I've added the same amount to both sides. Let's take a look at how this works. And one thing I'd like you to notice about this system, and this is very important, is that all the x terms are first, all the y terms are second, z terms are together, and constants are on the opposite side. If you don't set up your system like this, you're very likely to make a mistake. So we're going to go with this, and I'd like to have an equation at the top where x coefficient is 1. So I'm just going to switch equations 1 and 2 around. That was one of my operations that's allowed. So now on top I'll write x plus 3y plus 2z equals 1, and underneath that I'll write what used to be the first equation. Okay, so I've interchanged two equations. Now the next thing I want to do is to eliminate the x coefficients, or the x variables, from both of these equations. So I'm going to start with the second equation where the coefficient of x is 2. So I've got 2x plus y minus z equals 2. And I'm going to multiply my first equation by negative 2. So I've got negative 2x minus 6y minus 4z equals negative 2. And when I add those together, the x terms cancel each other out. I have negative 5y minus 5z equals 0. Okay, so now I have one equation with only two variables. I want another one. This time, I can see that the first equation and the second equation, or the third equation, have the same x coefficient already. So I'm going to just subtract this from this. So x plus y plus z minus x minus 3y minus 2z negative 1. X's cancel out. I have y minus 3y is negative 2y. Z minus 2z is negative z. And 2 minus 1 gives me 1. So now I have two equations with just y and z. So I'm going to copy this one under the other. And now I can look at these two equations. What can I do to solve those two? Well, one thing I could do, I could multiply this equation by negative 5. Let's do that. So that would give me 10y minus plus 5z equals negative 5. Now I'm going to add this equation and this equation. So I've got 10y minus 5y gives me 5y. Negative 5z and plus 5z are going to cancel out. And then I have 0 and negative 5. So negative 5. Then when I divide by 5, I end up with y equals negative 1. Now I'm not finished by any means. I have one variable out of 3. But I want to go ahead and write that solution that I got someplace where I won't lose it. So up in the corner here, y equals negative 1. Okay, now I want to look at some of the other equations that I had. Is there something I can do with y equals negative 1? Looking at this equation, I could rewrite this one, put the negative 1 in here, and I have negative 2 times negative 1, so positive 2 minus z equals 1. So this tells me if I move the z over here and I move the 1 over this way, 2 minus the 1 is going to give me 1 equals z. So I'm going to add that to my information up here. Z equals positive 1. Now I'm going back to this equation, x plus y plus z equals 2. And I'm going to rewrite that x plus y is negative 1 and z is positive 1 equals 2. Well, negative 1, positive 1 are going to cancel each other out, and I'm left with x equals 2. So now my ordered triple for this set is 2, negative 1, and 1. Always a good idea to check your solution, and I'm fairly confident because I use this equation to get my solution that this is going to work here, but check that it works in all three equations before you decide that that is your correct solution. The procedure that I used here is outlined in your textbook on page 276, and you can use it to work on checkpoint 1. You may have noticed that when we work a system of equations like this one, that the variables don't really change. It's just the coefficients that change as we manipulate the equations. So it would seem that it would be easier to work this system without the variables in there. And we can do that by using something called a matrix. A matrix is just an array of numbers that mirrors the structure of these equations. So the matrix for this system would look like this. We start with a square bracket, 2, 1, negative 1, and 2, and end with a square bracket, 1, 3, 2, 1, 1, 1, 1, and 2. Now it is important when we're making a matrix that we have all the x's first, and then all the y's, and then all the z's, and the constants on the other side. To show that these are the constants, we put a line here and call this an augmented matrix. We can work with an augmented matrix very much the same way that we did the system of equations in the last example. We can shift the rows up and down. We can multiply one row by a constant and add or subtract it with another row. Or we can just multiply the row or divide the row by a constant. You can practice using operations on matrices and converting from equations to matrices and back again in checkpoints 2 and 3. Now let's look at another system of equations. We've got x minus 2y equals 6 minus 4z, x plus 13z equals 6 minus y, negative 2x plus 6y minus z equals negative 10. Of these three equations, only the last one is in the correct format to be converted to a matrix. So we'll look at these other two and rewrite them in correct format. This first one, x minus 2y, that's okay. But the z term is over here, so I'm going to bring it over here, which will make it positive. and I can leave the 6 where it is. In this equation, starts with x, that's good. The y is over here though, so I'm going to bring the y back over here and make it plus y plus 13z equals 6. So I'm going to erase these first two equations. We haven't changed the value of anything in the equations when we rewrote them, so we're still good with that. Now we're going to convert this into an augmented matrix. -2, 6, -1, -10, 1, -2, 4, and 6, 1, 1, 13, and 6. And there's our line to show the augmented part. Now to work on this matrix, the first thing I want is a 1 up in this corner. So I'm going to take this second row and interchange it with the first row. So I have 1, -2, 4, and 6, -2, 6, -1, -10, 1, 1, 13, and 6. Okay, now I've got the 1 up there like I want. I'm going to multiply this row by 2 and add it to this row, because that's going to eliminate that x value there. I've got 1, -2. I don't change anything in the first row. I'm just going to multiply this by 2 and add it to this. So 2 minus 2 will give me 0. -2 times 2 would be -4 plus 6 gives me 2. And then 8 minus 1 will give me 7. And 12 minus 10 will give me 2. To get rid of this 1, I'm just going to subtract this from this row. So 1 minus 1 gives me 0. 1 minus -2 is going to give me 3. 13 minus 4 is 9. And 6 minus 6 will be 0. Now I see here that if I want a 1 in this position, I'm going to end up dividing by 2 and having a fraction, and although that's not horrible, just to make it a little easier, I'm going to interchange these two lower rows. So I'll make this 3 and 2, and I'll make this 9 and 7, and then 0 and 2. Now when I divide this row by 3 to get a 1 here, it comes out very nicely. 1, -2, 4, and 6, 0, 1, 3, and 0, and 0, 2, 7, and 2. Okay, moving back up to the top corner here, I have a 1 here with zeros underneath it, a 1 here, but I don't have a 0 underneath that. So I'm going to double this row and subtract it from this row. And again, I'll leave the first row the way it is. 1, -2, 4, and 6. Second row just the way it is. But now I'm going to double this and subtract it from this. So 2 minus double that, 2 minus 2 is 0. 7 minus twice 3, or 6, is 1. And then 2 minus twice 0 is just going to be 2. So while I was trying to get a 0 here, I had the added benefit of getting a 1 here. So now I have 1s on the diagonal, 0s underneath it, and I can rewrite this back into equations. And my first equation, I'm going to start at the bottom. 1z equals 2. Okay, simple enough. Now I can use this information to work on this equation. I have 1y plus 3z, but I know that z is equal to 2, so let's just put a 2 there, equals 0. So this is y plus 6 equals 0, so y must be negative 6. I'm going to write that up here. And then erase this. And now I'll look at this top equation where I have x minus 2 times negative 6 plus 4 times 2 equals 6. So this is x plus 12 plus 8 equals 6. And I know that 12 plus 8 is 20. So when I move that to the other side, I get that x equals negative 14. So now to write my ordered triple, I want to write it in alphabetical order. So it's going to be negative 14, that's the x, negative 6, and 2. So I've just solved the system of equations using a matrix. Pause the video now and work on checkpoint 4. If you prefer not to do back substitution when you're working with matrices, you can continue to eliminate numbers from the matrix until you have 1s on the diagonal and only 0s everywhere else on the left side. This is called Gauss-Jordan elimination. Let's take a look at it. I'm going to start with the matrix we stopped with in example 2. Okay, now we're going to work basically backwards of what we did before. We're going to use multiples of row 3 to eliminate the 3 in row 2. So to do that, I need to multiply row 3 by 3, negative 3. So I have a negative 3 here. And so here's my new matrix. I'm going to multiply this by negative 3, so negative 3 plus 3 will give me 0. Negative 6 plus 0 will give me negative 6. And then I leave this row alone, 0, 0, 1, and 2. to eliminate this 4, I do the same thing, except I multiply my last row by -4. So this time I'm going to start from the bottom. 0, 0, 1, and 2. I'm happy with that. 0, 1, 0, and -6. That's good. And I'm going to multiply this by -4. Okay, the 2 zeros are not going to change anything up here. I've got 1, -2. But -4 here plus the 4 up here will give me a 0. And 2 times -4 is -8. Plus the 6 gives me a -2. Okay, I'm almost where I want to be. The only thing I have to get rid of is this -2. So I will do that by taking twice this row and adding it to this row. So I'm going to copy the rows that I'm happy with. And I know for some of you this seems like a lot of work, a lot of writing, and it is. As you get a little more proficient, you might find that you don't need to write out every single matrix. I like to do it because I think it's easy to make a mistake and get rows and columns confused. So now I'm going to take 2 times this row and add it to the first row. Well, 2 times 0 is still going to give me 1 here. I have 0 and 0, so that's still 0. And then 2 times 1 plus 2 will give me the 0. And 2 times -6 is going to give me -12 plus -2, so -14. And now this is my solution set. And if you recall from our last example, our solution set was -14, -6, and 2. Write it as an ordered triple, alphabetical order, and you may use whichever method you prefer. Pause the video now and work on checkpoint 5. Just like in the last section, we can have dependent or inconsistent systems when we're working with matrices. Let's work an example to show this. Here's my system. Now, the first thing I think you might notice is that this system has 3 equations, but it only has 2 variables. So this probably increases our chances of having a system that's not going to be solvable. But let's proceed. I'm going to go ahead and make a matrix. And now we're going to proceed as we have in the past. I'm going to start by dividing this row by 2 or multiplying by 1/2. So now I have 1, 2, and 2, 3, 6, and 8, 2, 1, and 7. My next step is to multiply this row by -3 and add it to this row. 1, 2, and 2, Negative 3 and 3 is 0. Negative 6 and 6 is also 0. And then negative 6 and 8 is 2. And then I can write 2, 1, and 7. Okay, now I could go on working on this one, but there's something here that should clue you in that there's trouble. And that's the second row now. Because what this is saying is that x, 0x plus 0y equals 2. And we know that that's not possible for no x's and no y's to equal 2. So we can say that this is an inconsistent system, which in our last section we said represented parallel lines. At least two of these lines are inconsistent. So there's no solution here. Pause the video now and work on checkpoint 8. Let's use matrix methods to solve another system. This system of equations is very typical of what we might solve. There is no x term in the third equation, but if that bothers you, you can write in 0x. Everything's already lined up the way it should be, so we're ready to write our augmented matrix. We've got 2, negative 3, 4, and 6, 1, negative 2, 1, and 9, 0, 1, 2, and negative 12. Okay, I want to start with a 1 up in this top corner, so I'm just going to switch these two around, which gives me 1, negative 2, 1, 9, and then 2, negative 3, 4, 6, 0, 1, 2, negative 12. My next step is to get rid of this 2, so I'll take negative 2 times the first row and add it to the second row. So I take this row times negative 2. And remember, I don't put that in the first row, I leave the first row the way it is. It's when I double this, or times negative 2, and add it to the second row. That gives me 0. This is 4 minus 3 is 1. And this is negative 2 plus 4 is going to give me 2. And negative 18 and 6 is going to give me negative 12. Not doing anything with the third row just yet. But I do see that the second row and the third row are the same now. So that's an indicator that maybe something's a little unusual. Now let's go on and see how it goes. If I just continue, 1, negative 2, and I subtract the second row from the third row, I end up with zeros all the way across. And if I'm working now to back substitute, I have that 0 z is equal to 0. Well, z could be anything. So we don't have a definitive value for z, but we're going to continue to back substitute and use this equation now that says y plus 2z equals negative 12. And we're going to solve that for y, so we get y is equal to negative 2z minus 12. And that's as much as we can do with that. Going on to the top equation, let's do this over here. X minus 2y. Well, and instead of y, we're going to put in our expression for y. So that's going to be minus 2z minus 12. So this is x minus 2y plus a z equals 9. And what I want here is x by itself. Like I have here, y equals something in terms of z. I want x equals something in terms of z. So let's multiply out what we've got. Negative 2 times negative 2 is going to give 4z plus 24 here, plus another z equals 9. Well, I've got 4z and another z is 5z. So now I have x plus 5z. And if I subtract the 9, I would have plus 15 equals 0. But I want x by itself, so I'm going to move both of these terms back this way. And I get x equals negative 5z minus 15. So now when I go to write my solution, I write it this way. I start with my expression for x. So it's going to be negative 5z minus 15. And then my expression for y, which is negative 2z minus 12. And then lastly, just the z. So this is my solution set, which means if I pick a value for z, then I can find a value for y and a value for x. But I could pick any value for z and get different x's and y's, but they would all be solutions of this system. Pause the video now and work on checkpoint 9. For our last example, we're going to solve a system with 4 variables and 4 equations. And just a reminder or a kind of a heads up, this book does something a little unusual. It uses x, y, and z for the first 3 variables, and then w for the 4th variable. Many other textbooks would put w as the first variable. but in this one, W is the fourth variable. So be mindful of that. So I'm given an augmented matrix already. I've got 1, 0, 0, 9, negative 12, 0, 1, 0, negative 1, 4, and 0, 0, 1, negative 2, and 1. So this left side was not a square matrix, so I've got the diagonal and I've got the zeros here, but I also have that one extra column that I'm going to have to deal with. Okay, so if this is my reduced row echelon matrix, the equations I can get from this, remember this is X, Y, Z, and W. So this first equation would be Z minus 2W equals 1. And then this row would be Y minus W equals 4. And then the top row would be X minus 9 plus 9W equals negative 12. So if I were to solve these equations for X, Y, and Z, I would have that Z is equal to 2W plus 1, Y is equal to W plus 4, and X is equal to negative 9W minus 12. So when I write this out as an ordered set of 4, we'll start with X, negative 9W minus 12, comma, W plus 4, 2W plus 1, and then my fourth parameter is W. Okay, so this is the solution set for this system. Pick a W and find all these other variables based on whatever W you pick. This concludes this lesson, and you should now be ready for your homework assignment.